So in this video we're going to be talking about the Henderson-Hasselbalch equation and talking about buffer capacity and buffer range. This will kind of finish up our discussion of buffers for now, and then we'll move on to titrations in the next couple videos. So we're going to talk about what makes a good buffer and what kind of range they can buffer over in terms of the pH range. But first we're going to start off with the Henderson-Hasselbalch equation. You can find this information on page 849 of your text. The Henderson-Hasselbalch allows us to kind of reliably estimate or calculate the pH of a solution as long as it is a buffer solution. So we have to have a weak acid along with its conjugate base present. If we don't have that buffer solution, then we can't really use the Henderson-Hasselbalch. So what we're going to start off with is our weak acid dissociation in water. We should be getting pretty automatic at this again, where our weak acid HA will dissociate into water and form H3O plus and A minus. We can write our equilibrium expression for this. Ka is equal to the concentration of the H3O plus and the concentration of the conjugate base over the initial weak acid concentration, or I guess equilibrium weak acid concentration. I can rearrange this so that we have the concentration of H3O plus. After all, we want the pH, so we can rearrange this so that we just have the H3O plus concentration on the one side of the equation. On the right hand side we would end up with Ka times HA, or concentration of HA, over the concentration of A minus. So now the H3O plus concentration is just dependent on the weak acid equilibrium constant Ka times the ratio of the weak acid divided by its conjugate base. So what we're going to do is we're going to leave yourself some room and we're going to rewrite this down here. And since we want pH, and all we have to do to get the pH is take the negative log of that H3O plus concentration, we're just going to take the negative log of everything so it all remains equal. And so on the left hand side of the equal sign we just end up with pH is equal to, and then we have Ka times HA over A minus, and we have taken the negative log of that. With our log rules, whenever we have a multiplication, that ends up just becoming a addition problem. So we'll have, and because it's a negative log, we're going to distribute that negative sign. So what we end up with is the negative log of Ka minus the log of HA over A minus. So again, the negative log of the H3O plus concentration, that just turns into the pH. The negative log of Ka, if we remember what the negative log just means, that just means the P sign that we put in front of H, so this would end up being the pKa. And we're going to leave this last term alone, but we're going to rearrange it really quickly. We're going to flip A minus over HA, which is really just multiplying by negative 1. And so we end up with the final equation, the Henderson-Hasselbalch, which is pH is equal to pKa plus the log of A minus over HA. And so what we can do, as long as we know the Ka of a weak acid and we know the concentrations of the weak acid and its conjugate base, remember those two have to be there, otherwise this won't work out. But as long as we know the concentrations of those two in the buffer, we can calculate the pH of that buffer. So that is the Henderson-Hasselbalch equation. So if we go back to problem 19.1, there's another video on that. If you go back to that problem and look at part B, the concentration of the HClO, the weak acid, after we did a sodium hydroxide addition, the concentration of the HClO was 0.48 molar. And similarly, after that HClO addition, the concentration of the ClO minus, the conjugate base, was 0.62 molar. We just need to find the pKa because we were given the Ka, so we know the pKa is just the negative log of Ka. And in that problem, the Ka was 2.9 times 10 to the negative 8th. So we can just say pKa is equal to negative log of 2.9 times 10 to the negative 8th. And we end up with a pKa is equal to 7.54. So now finally, to estimate the pH quickly without having to do the ice table or whatever, we just end up with 7.54 plus the log and this is the tricky part. We got to make sure we use the correct concentration in the correct spot. The concentration of the conjugate base, A minus, or ClO minus in this case, was 0.62, and the weak acid was 0.48. After we run all that and run that into our calculator, we just get that the pH is equal to 7.65, which is roughly the same value as we got by doing the full ice table and estimation and everything. So that saves us a lot of work and a lot of steps. Next, we want to talk about what makes a good buffer. In order to use the Henderson-Hasselbalch, we kind of have to know if we have a good buffer and what that means. So for our buffer capacity, that's going to talk about how much acid or base that buffer can absorb before it is not a buffer anymore. So we say the more concentrated the buffer, equals a higher buffer capacity. And that's just saying that the more moles we have of weak acid and its conjugate base in our buffer, that means it can absorb more strong acid or strong base before we start running out of either one of those components. So we say it can absorb more moles of acid or base. So for example, if we have the weak acid concentration equal to the conjugate base concentration, and that's equal to like 1 molar, that's a good buffer. That can absorb a lot of moles of strong acid or strong base before we start running out of those components. If, for example, we have the weak acid concentration equal to the conjugate base concentration, and it's like 0.01 molar, that's not very good. It can't absorb much acid or base before it starts running out. And the closer their relative concentration, so in the previous examples of the good and bad buffer I just gave you, we automatically set it up so that HA and A minus were equal. And we try to do that because the closer their relative concentrations, the better the buffer. Or we say it has more buffer capacity. So again, for example, if HA is equal to A minus, that's a good buffer, as long as the concentrations are high. And for example, if concentration of HA is much greater than the concentration of the conjugate base, or if the concentration of HA is much less than the concentration of the conjugate base, those are bad buffers. So that kind of leads into this last discussion about buffer range. How far can the buffer act as a buffer before it's no longer able to keep the pH from changing rapidly? So we just kind of arbitrarily have set a range where we say the concentration ratio, so again this comes from the Henderson-Hasselbalch, we're looking at the concentration ratio of the conjugate base over its weak acid. If that is a factor of 10, if we go back to the Henderson-Hasselbalch, we looked that the pH would be equal to pKa plus 1 log unit. So the log of 10 is just 1. So if the concentration of the conjugate base is 10 times higher than the concentration of its weak acid, then the pH is going to be 1 pH unit above the pKa. And similarly, if that ratio, A minus over HA, is equal to 0.1, so that means that the concentration of HA is 10 times greater than the concentration of A minus, then the pH is going to be equal to pKa minus 1, because the log of 0.1 is negative 1. So we say a buffer has a usable range around plus or minus 1 pH unit of the pKa. So because the pKa is based on the buffer conjugate acid-base pair that we're using, by changing the weak acid and its conjugate base, you're going to be changing Ka, so you'll be changing the pKa. So each buffer system will have a different pKa or pH range that it can buffer around. So for example, if we look at our acetic acid acetate buffer, the pKa for this system would be 4.74. Notice that's much different than the pKa of the chlorate that we were talking about in the earlier case. These are a much weaker acid. The HClO and ClO- are weaker acids and bases than the acetic acid is, so its pKa is higher. Remember, a higher pKa means a weaker acid. So back to this example, with our pKa about 4.7, that means it can buffer from a pH of 3.74 to a pH of 5.74, so plus or minus 1 pH unit of the pKa. So if we go back and look at a pH titration curve chart, we kind of talked about this when we were doing the titration curve problem, but we noticed that the pH will rise sharply at the beginning and then it'll kind of level off, and then as we get closer to the equivalence point it rises sharply again and then it levels off. Within the pKa range, so if we look at the equivalence point, within that pKa range there is what we call the buffer region. And that region is simply from where we have a pH change of plus or minus 1 pH unit around the pKa. So if we remember, we have the half equivalence point, we have the full equivalence point and then the half equivalence point, and these are all roughly drawn, so pardon the scale. At the half equivalence point, the pH is equal to the pKa, so that would be our pKa right there. We go plus or minus 1 pH unit above and below that, and that would be our buffer region. Anywhere outside of that, notice the pH changes very rapidly. And that's it for our discussion about buffer capacity and buffer range. From here on out, we'll be dealing with at least for the last part of this chapter, before we get to solubility, we'll be dealing with titration curves and calculating the pH in a titration curve. At some point during those calculations, we will have a buffer and we will be able to go back and use the Henderson-Hasselbalch to save ourselves some time in those calculations.